Today I'm going to try to keep it short and sweet. That's always a joke with me because I just get long-winded, but I apologize for that. I appreciate you looking at it. Hopefully it helps a little bit. But today I'm going to take a few minutes and we're going to look at comparing two blower boards or air handler fan control boards. I've done this in the past with the Goodman. The Goodman air handler board is, so many units out there, so many people looking up Goodman stuff. I do it all the time as well. But this is not the only fan board out there. But what I tell guys that I come in contact with trying to get into the service side of this field is this is the thinking side of it. This fan board from a Goodman that we have here, I'll throw a link up to the video if you hadn't seen it. Appreciate you checking it out if you have. But this fan board, the same logic that you use to learn about it and to troubleshoot it can be applied to this Rheem board. We've got two air handlers side by side. I've got a Goodman and a Rheem, and guys are looking at it crazy almost because it looks different. And that's going to be typical of service work in the field. You have to take a few minutes and look at the diagram, look at the unit, the wiring, and figure out what's going on. So just going to address a few things, try to clean it up a little bit and make it worthwhile. But this Rheem board is really not that hard. Okay, you'll typically see these with a PSC motor. So you're going to have like a 3-speed PSC motor or a 2-speed. The Goodman units that we have here have a high, medium, and low speed. So you'll see like a black wire for high, blue for medium, and red for low. I do have a Rheem that has a 3-speed motor in it, and I've got one that's got a 2-speed motor in it. So either way, you're probably going to see this with a PSC motor. All right, so look at the Goodman video if you haven't. I like it, but you know, I'm weird like that. So this is a Rheem. You can see the part number up here. It's a 47-100-43605, and I'm sure there's some superseded version where it's been replaced by an 06 model or you know whatever it is. So, but that's the part number right here in this little black square on the board. If we look at it and liken it to the Goodman, we're going to see some similarities. We're going to see this black relay here. That's the physical fan relay. We're going to see this fuse. That's the 5-amp fuse. Anytime you see a fuse, it's there to protect the 24-volt transformer circuit. The one thing that the Goodman board had, right? I'll flash it back real quick. The one thing that we had on the Goodman, we got the relay, we got where the fuse goes, okay? But the Goodman board did not have these plugs soldered into it. We actually had some 1/4-inch male spades to connect to, and it was pretty much individual wires. So that's something different that this Rheem board does, but the plugs, is still a wire there, okay? So we've got a smaller plug and then this larger one where this red is, okay? So we'll take just a second and we're gonna go through these and kind of identify them real quick. Maybe you'll pick up something, right? This fan relay right here, if you look at it, you'll notice, hopefully you'll notice one thing right away, that the Goodman relay had a common, normally open, and a normally closed circuit in that relay. This is typical of the brown relay, the 9340, that you will come across in the field. But this Goodman, or this Rheem air handler board, it only has like a common and a normally open. They don't even label it like the Goodman board did. They don't even label it. It's just one switch. They took this part out. You'll see like it's the same profile, but they took the normally closed switch out. That's going to be important later. Okay. With the fan stuff, you'll notice that there's also a couple park terminals that the Goodman has off to the side of their relay. You don't see that on this blower board. All right. So when we're not using, if I were to have high speed on this fan relay coming out and powering everything, what do we do with medium and low? On the Goodman, you had a place to put it, but on the Rheem, you don't. You just have to dress those up, zip tie them or cap them. God knows you don't want that wire to touch a copper coil or aluminum coil because it's probably going to short. You know, and you wind up having some problems. Hopefully not a leaky coil, but you could, you know, blow the fuse, trip the breaker or whatnot. So other than that, like I said, we have some standard stuff. Transformer R, this is where power comes in. This is the one red wire coming from the 24-volt transformer. It goes in here. And what it's going to do is it's going to feed into this 5 amp fuse or 3 amp fuse. If the fuse is good, it passes power across, and then that circuit within the board is going to go straight over here to this R. All right. If we flip this over, if you were to follow, this is the transformer R. This circuit, you can see it goes into the fuse. If the fuse is good, then it passes power, up here on the fuse, passes power back. When that 24 volts comes back in, it goes through some diodes and stuff to do some work over here. We don't tend to get that deep. We're not electronics gurus, but I have enough sense to follow a line. So that 24 volts, you can see it just goes down here, and it goes into that first of 5 pins, right? Well, that first of 5 pins is the R. This white plug, this is R going out to your thermostat. This is common coming back from your thermostat. We have a G coming from the thermostat, and your W1, W2 for your sequencer heat relay, whichever you have or whatever you want to call it. These are coming in. So these terminals here, or this plug here, is going to deal mainly with your thermostat connections. All right. So and most of them are coming back in. Okay, if you follow my logic and my flow of power, this G is coming back in along with the W's to do something, to tell the board to work, to tell the sequencer to work. All right. So transformer R comes in. Transformer common, for me, that's going back out. All right. You can see here we got a transformer common, just like on the Goodman board. I've got a transformer common and a regular common. Well, we've got that here. So transformer common, regular common. We've got a common that's the part of the thermostat connection group, and we've got a common way over here. Common is common is common. It's all the same. So if we were to flip this over, common is the 3rd pin on this red plug, and I can see it here. 1, 2, 3. It's the 3rd pin. It loops over to this common, right, which backtracks to the transformer common and the regular common terminals. So don't be afraid to look at these boards and flip them over. A lot of times guys will flip them over and they'll find a burn spot where somebody puts 120 volts or 240 volts onto a low voltage circuit, and it just fries the back, fries the circuit board. So lots of similarities. Some of the biggest are this W and W2 or W1 and W2 connection. Why do I have that on the board? Why don't I have part terminals? Why do I have just one switch on this fan relay? That kind of goes together, the W and the fan relay stuff. The part terminals, I couldn't tell you. I wish they'd just solder in a couple dummy spots right here. Doesn't take up any room. You got plenty of space for it. And it would, kind of dress it up a little bit. But the reason that, to me, that this fan relay doesn't have a normally closed switch is because it doesn't need one. If they needed one, they would have provided it. This relay has to close every time the fan needs to come on. There's no other way around it. The Goodman, I've got a normally closed circuit, which is like not even having a switch there. The circuit is closed. It's complete already. This relay doesn't have it. And for my simple little thinking is because anytime power comes in on this W1 or W2, whether I have a call for the fan on the G circuit or not, this brain knows that when I send power out to the heat sequencer or contactor or whatever, I'm going to turn on the fan with it. I don't need a normally closed on this relay because it doesn't matter if I've energized G or not. Anytime that I see W on this board, when it comes in here, as W loops around and goes back out to the actual sequencer, I know to close that relay and turn the fan on. Goodman doesn't have a W on their board, and it's because you don't need it. I don't need a W on this board to run the heat. This is a fan board, for God's sake, right? So why would I have a W here and be missing a terminal off my fan relay? It's simple. They're connected somehow, right? You gotta like CSI this thing. Anytime I get a call for heat, I know to turn the fan on. We have to have airflow across our elements, otherwise we wind up tripping limits or fusible links, or God forbid we actually have something go wrong with the element. Point being, they're going to energize that fan no matter what. So that's the reason we don't have that. So on this air handler, where Goodman has a purple wire coming through to the normally closed from off of the heater circuit, I don't have that with this Rheem. It's more simplified. It's very easy to understand as far as the heater wiring, but the fan is where people are missing, because this normally closed safety or normally closed switch is like a redundant safety. I can piggyback off of the high voltage heater circuit and get the fan to come on regardless. So anyway, we'll look at that, and we'll go out into the shop. If you have any questions, please let me know. But they are essentially the same board with just a couple modifications. They're like 90% the same, okay? So let's get into the shop. We'll do a couple voltage checks and do a look at the actual air handler itself. So, all right, here we go. And I'm going to show you, I'm going to walk you through a couple different checks. I've already got the air handler open. Here is our circuit board that we're talking about. I've got the power on. Real simple, right? If you're going to check power coming into the board, right, this board has to have power in order for it to do its job. It doesn't have to have power on some boards, right? It doesn't have to have power to necessarily let something flow through it on a normally closed switch, but in order for that brain to think and perform its function, it's going to have power. So first things first, you always prove power. We're always looking for power on electrical problems. So I'm going to do the transformer R to transformer C. Okay, and you can see there I've got 28 volts. Okay, so we have power to the board. Now the thermostat is off, so there's nothing going on, and I'm going to take this opportunity. We're going to refresh a couple little steps, right? One is the hopscotch. We always reference one side of power to the other one. So this fuse circuit, if you didn't just look at the fuse, or let's say that it was positioned so you couldn't see it being blown or whatever, I will leave one lead on common, and this transformer R, right, it brings power from the transformer into the board on that terminal, and then the circuits on the board go to the fuse. So I can check power going into the fuse. Okay, so I still got 28 volts. If the fuse is good, I'm going to go across the fuse to the other side. Hey, look at that, my fuse is good. And that's going back in the board, and is going to go over here. I'm going to swap leads, but I'm going to keep one on that transformer common. It's going to go over here to this R that's leaving our circuit board. Okay, so this is a very tight plug. You can't get in there. Let me show you what I would do in this instance. All right, here's what I'm going to do. There are test leads that have the screw-on alligator clip with it. I don't have that, so I'm going to do the poor heat and air guy way. I'm going to take an alligator clip and clip right there to my transformer common, and I'm going to put it on the black lead and just lay it out the way. Okay, so anytime I'm checking voltage now and I'm following the hot circuit, the R into the board, then into the fuse, then out of the fuse. Okay, you can remove this plug and check certain things. Okay, you have to be mindful of what you are checking. So if I was going to check power, I could easily pull this plug and check R, and since my alligator clip is on the constant always, or on the common always, then I should get voltage, or I would see if the board is actually allowing power from the fuse across the board so it can go to my thermostat. But a lot of times when you unplug the plug, there's other things later that don't work. So I'm going to take a small piece of thermostat wire. You don't want to jab your lead down in there. You can bend things and inadvertently mess things up, of course by accident. But what I'm going to do is I'm going to take a piece of thermostat wire, and they make specialty leads like this. I'm going to stick one on R. So if I wanted to see if this board as is sending 24 volts out, I would check here, hey, 28 volts. So I know that the board is doing the proper job and sending it to the thermostat. Now likewise, that's 1/2 of power to the thermostat. If you wanted to see if the common was good, I could move that wire up to the common terminal, and I could check it against the R. Okay, so I know I've got 28 volts here. I've got a good R circuit through the board, and I've got a good common back. All right, and that makes things easy. All right, so a little piece of thermostat wire, an alligator clip. When I'm checking 24 volts, I never move it off of that transformer common, because that is the end of the circuit. That is my other side of power. Okay, so I'm going to go ahead. I'm going to turn the fan on, we're going to turn it on in heat, and we're going to do a couple checks. And but really, that's how I would prove power in the board and also the power leaving the board. Now we're going to look at the G and the W circuit. All right, so I'm going to turn the electric heat on. All right, the fan just engaged. Now, on this one, the fan coming on does not necessarily mean that G got energized. So what I would do is I would take and kind of move that wire on the plug, and I'm going to put my little thermostat wire on G. Now, if the thermostat is sending 24 volts, which it's not, it's 0, why is my fan on? Okay, this goes back to the whole purpose as to why the heat, the W circuit, is on this board. So I'm going to move this wire off of the G and plug it in on the W circuit. And if we have 24 volts on this, which I do, so my heater should be on. We can check our amperage with our clamp meter here. So I've got 17 and a half amps or so on my electric heat, and I don't have a 24 volt call for G. Okay, so what's bringing it on? It's the W circuit. So one lead on the transformer common and the other one on the W1, and that proves power into my board. I could prove power out of my board. If you were not getting your heat sequencer to come on, you could easily put this thermostat wire inside that little plug, and I get 27 volts coming out of the board. So this white plug, the smaller plug, is your thermostat connections. It is power leaving to power the transformer and also to come back in on the G and W circuits. This bigger plug up here with the red connections on the actual board, this is the power going out. So that W is leaving out of the board. I've got 27 volts. I could easily go up top to the heat sequencer or heat relay and check where the actual white wire went into that particular coil. I've got 27 volts. So part of your troubleshooting there. All right, and that's pretty easy. As far as your high voltage, I would not stick the thermostat wire in the high voltage portion of the relay. Usually those are insulated terminals like here. They are not necessarily going to give you enough room to put in there. You could try it, I guess, if you really want to, but I usually don't. If I want to see if power's going in, then well, for one, we can hear it, so we know it is. And since this is the only switch on this particular relay, it's pretty safe to say that that switch is closed when it's supposed to. While I've got my, matter of fact, let me I'll turn the electric heat back on. All right, I'm going to do this real quick, just to show you if I wanted to check this relay in place. Now, the electric heat is on. All right, and that, of course, the 24 volt signal is actually keeping that blower switch closed. But let's say that your blower wasn't actually running and you wanted to check the switch. A lot of young guys that I see, that you think that you have to, when you pull one wire off, you have to pull them all off. I can leave all the low voltage connected to this board, and if I'm just troubleshooting that switch on that relay, then I can use continuity, and I'll set my meter to continuity, and I've got it with my leads. But if I wanted to check this switch, maybe it's a burn up switch, there's some carbon or something in there, I could unplug this, right? And I take the high voltage off of the switch. So if I wanted to see if the switch is actually closed, I could do continuity through there, and by pulling the W off of it, that switch should open up, in a few seconds or whatnot, and you could redo it again. Okay, so don't think that you have to keep all the wires on. You could easily pull them off to check continuity. You're not going to check necessarily voltage, because you've pulled the voltage off. All right, so just another little tidbit. Hopefully it helps. Of course, this is what happens when you don't have the park terminals. You have just dangly wires. We decided to put some insulated terminals in the end. That way it doesn't touch that coil or the cabinet or anything like that, because these leads, even though you're not, if I grab the right one there, these leads are still electrically hot even though they're not connected to anything. They're all part of the run winding on this PSC motor, so when one gets power, they're all going to have power on them too. So anyway, that is pretty much it. Simple voltage checks: power in, power out, the G back to the common for the transformer, W back to common. Of course, if you got 24 volts on W leaving the board, it should go to the heat sequencer. But if I were going to replace this board, I could replace it with a Goodman board. I could replace it with a relay. I'm not going to go into that. I think most people that, if you've seen the other videos, whether it's mine or someone else's, you probably get the idea of it. But I could put a Goodman board in place of this. Of course, it's not going to plug up right, but as far as wire connections and the thought process behind everything, it would work. All right, I could make it work. I could put some terminals on it and you know, make it look good if I had to, because the boards are essentially the same. The only thing that doesn't work on the Goodman board, or isn't there, is the W. And I could easily cut this, strip it back, and put a wire nut connection, you know, to the W wire coming out of the thermostat. So it's fairly simple, but hopefully you get the idea. It's another air handler board, so they're all meant to control the fan. Tell me what you think. If you got any questions, let me know. Until next time, we're gone.